Okay guys, welcome back. We're going to start 9.4 on geometric sequences and series. Something I would encourage all of you to do first is you should be writing down all of these notes. So in just a sec here, you can pause this video, write down all these warm-up problems, and I'm going to give you a couple minutes to work through them just by pausing the video. Pause the video, work through these questions, and then I'll put the answers up and I'll go through every single one of them with you guys. Something else that might help is put your iPad on airplane mode. Put it on Do Not Disturb so you don't have your notifications popping up. I was just trying to record one of these and forgot to do that. It's extremely distracting. So use that as a way to help you focus here. These will be short, 20-minute lectures. So why don't you guys go ahead and pause. You can write down these problems, go ahead and work them out, and I'll put the solutions up after you unpause. Okay, so for number one, hopefully we all noticed that this had a common difference in between consecutive terms, meaning this was an arithmetic series. So our explicit rule would have been a sub n equals 3 times n minus 1 plus 8 if you're using the first term in the sequence. If you wanted to use term 0, that would be a sub n equals 3n, and then just go back to term 0, which would be subtracting 3, so plus 5. Okay, either one of those explicit rules work. Okay. For number two, you should have noticed that this was not arithmetic, meaning no common difference. It wasn't multiplying, which is a geometric sequence we'll talk about today. But really what you needed to notice was the denominators were 2 on most of these. And if you rewrote the second and the fourth terms with a denominator of 2, we can rewrite 2 as 4 over 2. We can rewrite 8 as 16 over 2. Now, hopefully you notice that in this rule, you needed 2 in your denominator, and every numerator should be a number that you're familiar with or you've seen before, because these are perfect squares. And perfect squares means you need n squared somewhere in that rule. And then always, these are like functions. You plug in an input and you get an output. Go check to see if this works. If I plug in 3, we should get 9 over 2. A sub 3 equals 3 squared over 2. We get 9 over 2, so that checks out. All right, let's not circle that. Let's circle our rule, because that's what the directions we're asking us for there. Okay, great. 3 and 4. Now we're writing the first 5 terms of each sequence. And guys, just a reminder, if I'm going too fast, you can always pause the video to get caught up on what you need to write down. That might be helpful when we get into the notes for 9.4 in just a sec. For 3 and 4, the first 5 terms of each sequence. Number 3 was a recursive rule, a sub n minus 1. So when we start with 1, I'll always have to give you the first term in a recursive rule or recursive sequence. And then the second term comes from the previous term, negative 1 times 2 minus 12. And if you work that out, that would just get you a negative 14. So then the third term would come from the previous term, multiplying by 2 and subtracting 12 to get you negative 40. Fourth term, negative 92. And last term, negative 196. Just the first 5 terms. I'll always have to give you the first term in a recursive rule. If you guys have any questions on answers I'm getting, or if I might have made a mistake, just write them down, and on office hours on Thursday, I'll go over details on how the Google Meet's going to work. You can ask them there, okay? Great. Number 4, this is an explicit rule, so when you're asked to find the first 5 terms of an explicit rule, just start by plugging in 1, so that would give us 1 squared minus 2 times 1, which gets us 1 minus 2, so negative 1 was going to be our first term. And then plugging in 2. If we plug in 2, that would have got us 0, because 2 squared would be our 4, minus 4 gets us 0, and so on and so forth. Plugging in 3 would have gotten us 3, 9 minus 6. Plugging in 4 would have gotten us 8, 16 minus 8. And our last term would have been 15. So our first 5 terms of this explicit rule. Great. Our last 2 last two, these were series. So we were evaluating series. Number 5, if it's already written in sigma notation for you and you're not asked to expand, you can just plug this into your calculator. I've showed most of you in class how to punch this into your calculator. Remember, if you have a newer calculator, you hit math and then scroll down. But now if most of us are on our iPads, you can always just hop onto Desmos, and you're actually going to want the graphing part of Desmos. And the reason you want to plug this into your calculator instead of expanding it out, because remember the total number of terms here, upper limit minus lower limit plus 1. So this is 25 total terms in this series. You don't want to try and add 25 terms by hand. So let's just punch this in. You're going to hit this functions over here on the right and go down under miscellaneous to where you see sigma. And then you can enter everything for your rule. Lower limit, upper limit. Oops, that needs to be a 4. And then your rule. And always put it in parentheses. Always put it in parentheses. 0.5n plus 5.5, which gives us a sum of 337.5. Okay. Number 6, a little more work because you don't have the rule. So if you were to solve number 6, I would put it into sigma notation first by finding your rule. We do know our lower limit's 1 and our upper limit's 17 because this is asking for the sum of the first 17 terms in this series. And the rule should have been, well, we should notice that this is plus 5, plus 5, plus 5. So a linear or arithmetic series, our rule should be 5 times, you can use n minus 1, or you could just use n if you want, less parentheses. And if you're using just 5n, then you need to go back to term 0, which would be minus 11. And then again, punch this in on your calculator or on Desmos. 117, plug it in parentheses, minus 11. Close them, and we get a sum of 578. So once again, when it asks you to just evaluate means write it in sigma notation and tell me what the sum equals for that given series. If you're asked to expand, then you need to write it out like this. Expanding means taking that sigma notation and expanding it out. And I won't ever ask you to expand for something more than, say, 7 or 8 terms. Okay, let's move on to geometric sequences and series. So if you remember last time I